from wooden machines powered by human muscle to giant steel monsters capable of lifting entire buildings. This is the 2,000-year evolution of cranes, with Big Carl as the latest breakthrough, and a look at what comes next. Around 500 BC, ancient Greek engineers began experimenting with levers, ropes, and pulleys. These early machines didn't look impressive, but they quietly changed construction forever. By combining multiple pulleys into a single system, one person could lift loads far heavier than their own body weight. This principle is called mechanical advantage, and it remains the foundation of every crane in existence today. The Greeks and later the Romans developed early cranes known as the trispastos, pentaspastos, and polyspastos. Their names sound complex, but the idea was simple. More pulleys meant more lifting power. A trispastos used 3 ropes, a pentaspastos 5, and a polyspastos many more. These Roman cranes could lift several tons and were used to build temples, bridges, aqueducts, and massive stone monuments that still stand today. However, most of these cranes were made of wood, powered by humans or animals and fixed in place. They were slow, limited in movement, and physically demanding to operate. While pulleys solved the physics problem, they didn't solve the power problem. Human muscles could only do so much, and as construction ambitions grew, builders needed stronger solutions. Fast forward to the Middle Ages, roughly between 1000 and 1500 AD. Europe entered an era of massive construction. Cathedrals rose higher than ever before, castles dominated landscapes, and growing cities demanded larger and more complex structures. To meet these demands, builders introduced one of the most iconic machines of medieval engineering: the treadwheel crane. Imagine a giant wooden hamster wheel, large enough for 1 or 2 people to walk inside. As workers walked forward, the wheel rotated, winding a rope around a drum and lifting heavy stone blocks upward. The heavier the load, the slower and more carefully the workers had to move. The physical reality of this work was brutal. Workers spent hours inside rotating wheels, maintaining balance on wooden planks, while carrying the risk that a misstep, a broken rope, or a failed joint could send the load crashing down. Despite this, treadwheel cranes were remarkably effective. They became common sights on cathedral construction sites such as Notre Dame, Chartres, and Cologne Cathedral. Many were installed directly inside the buildings as they rose, sitting on wooden platforms that were lifted higher floor by floor. This marked an important conceptual shift. These cranes didn't just help build structures, they grew along with them. It was an early form of vertical construction support, a core idea behind modern tower cranes. Another crucial development appeared during this period: basic braking and locking systems. Wooden ratchets and pawls allowed operators to stop loads mid-lift and prevent them from slipping backward. This may sound simple, but it transformed cranes from risky lifting devices into controllable machines. For the first time, builders could lift heavy loads smoothly, stop precisely, and place stones exactly where masons needed them. Large-scale vertical construction became practical, repeatable, and reliable. But walking inside wooden wheels could only take construction so far. As cities expanded and global trade increased, a new source of power was needed. The world was about to discover steam. The Industrial Revolution of the 1800s changed everything. Muscle power gave way to mechanical power, and wood gave way to steel. Cranes evolved from temporary construction tools into permanent industrial machines. Steam engines allowed cranes to lift heavier loads continuously without exhaustion. Engineers such as William Fairbairn designed early steam-powered cranes for dockyards, rail yards, and shipbuilding facilities. Steel structures dramatically increased strength and durability, while a major breakthrough came with the introduction of steel wire cables. Compared to ropes or chains, steel cables were stronger, lighter, more flexible, and far more reliable. Steam cranes could lift dozens of tons, but they were not perfect. They were slow to start, required constant fuel, and needed skilled maintenance. That challenge opened the door to the next revolution. In the early 20th century, electric motors replaced steam engines. This shift didn't look dramatic, but it fundamentally changed crane operation. Electric cranes were cleaner, faster, quieter, and far easier to control. They could start instantly, stop precisely, and work for long periods without constant supervision. At the same time, hydraulics entered the scene. By using pressurized fluid, cranes gained smoother motion, finer control, and greater lifting stability. Cranes were no longer brute force machines, they became precision tools. Another critical innovation emerged: counterweights. By balancing the load with heavy masses placed opposite the boom, cranes could lift far heavier objects without tipping over. Counterweights transformed stability and allowed cranes to grow taller and more powerful without simply making every component stronger. As cranes became more complex, a new profession emerged: the crane operator, or crane machinist. No longer a laborer providing raw muscle, this role required technical skill, spatial awareness, and deep understanding of machine limits. Operating a crane became a specialized, respected profession. This evolution arrived at the perfect moment. Cities were growing upward. Steel frame construction made skyscrapers possible, and cranes had to keep up. Modern tower cranes were born. They became modular, allowing transport in sections and assembly on site. Even more impressive were self-climbing cranes, capable of lifting themselves higher as buildings rose beneath them. By the late 20th century, cranes reached incredible heights and lifting capacities, but safety became the next major challenge. As margins for error shrank, computers stepped in. Load moment indicators, sensors, and onboard computers continuously calculated load weight, boom angle, lifting radius, wind speed, and structural stress. Cranes transitioned from skill-based estimation to data-driven precision. Experience still mattered, but every decision was now backed by real-time information. Manufacturers like Liebherr and Potain refined tower crane designs into the industry standards we recognize today. Construction became faster, safer, and more reliable. But for extreme projects, nuclear power plants, offshore platforms, and mega-industrial facilities, tower cranes weren't enough. A new class of machine emerged: the super heavy lift crane. The most famous example is the Saren's SGC 250, better known as Big Carl. With a lifting capacity of around 5,000 tons, Big Carl pushes the limits of what can be achieved in a single lift. As a ring crane, it rotates on a massive circular track rather than a slender mast, reflecting decades of advances in load distribution, stability, and modular engineering. So what comes next? The future of cranes isn't just bigger, it's smarter. Automation is already assisting operators. AI-based load planning can simulate lifts before they happen, optimizing every movement. Electric and hybrid cranes are reducing emissions, especially in cities where noise and pollution matter. After 2,000 years, the goal hasn't changed: lifting more with less effort and less risk. But the tools have evolved from human muscle to intelligent machines, and the next evolution is already taking shape.